What's going on, everybody? Welcome back to Everything EE. Today we're going to be talking about finding a transfer function of a circuit. Thank you for coming by, and remember to like and subscribe. Here we have VI, which is a voltage source here. We have R1, which is 2 kilo ohms. We have C, which is 500 nanofarads. We have R2, which is 1K, and RL, our load resistor, that's also 1K. And then we have V out coming from across the load resistor. All right. When I approach these problems, I like to leave things in terms of their labels. So R1, R2, RL, and C, along with VI and VO. And I'm going to use that to keep things really clear. And then at the end, I can just plug in their actual values. Okay. So the first thing here, right? So we want the transfer function. And we usually write transfer functions as h of s. And what the transfer function is the relationship between the output voltage over the input voltage. Okay? So that's basically the gain. What are we gaining from this circuit? What's the ratio of the output voltage relative to the input voltage? Okay, so that's what we're looking for. So let's start thinking about this. What does this circuit sort of look like? Well, if you're not sure, we can break these up into two pieces. So we can kind of break this up here. So on the left side of this red line, we have what looks like a voltage divider, basically, right? We have R1 and then C, which we can call the voltage here V1. And you might be thinking, well, don't we do voltage dividers with resistances? Well, yes. And capacitors do have not necessarily what we call resistances, but they have impedances, which is a type of resistance. Um, and their impedance is based on what frequency is passing through there. So for all capacitors, we have the identity, or we can define their impedance as Z, which is for impedance, and we'll call it ZC is equal to 1 over SC. So that's going to be the impedance that we're going to use. The C is just the capacitance, so it's 500 nanofarads, and this S represents a piece of the frequency plane. So S is actually, not to get you guys too confused yet, because it's not a huge deal right now, but S is really J omega. Omega is the frequency, and J is the imaginary part of the impedance. Okay, so let's just get rid of that for now so we don't get confused. Let's just focus on a capacitor's impedance can be defined as 1 over SC. And here we have a voltage divider, right? So we have this voltage V1 going across this resistor, and we have R1 as the other part of this voltage divider. So let's take this step by step. Let's go ahead and solve for V1. Solve for V1. Okay. So let's redraw this circuit to what we have, and let's remind ourselves um, what a voltage division circuit looks like. It's going to look like this. You have some VS or V source. You have this R1, and then you have this R2, and then you have VO across this resistor. And we can describe VO is equal to R2 over R1 plus R2 times the input voltage, so Vs. So we're going to use this here to benefit us for this left-hand side of the circuit. So let's redraw similar to what we've drawn over here for the voltage divider circuit. So we have this VI, we have R1, and then we have this capacitor, and its impedance is going to be defined as ZC. Okay? So our relationship using voltage division is coming from over here, right? We have VO, right? So we have the same thing, but our VO is V1. So let's write it. So V1 is equal to ZC over R1 plus ZC times VI, the input voltage. So now that we've got V1, let's go ahead and move on to the right side of this circuit, where we have another voltage divider. So we have R2 and RL in a voltage dividing kind of setup. So let's take it again as a voltage divider problem. So, and we'll solve for V out. So solve for V out. And we have this circuit here. If we just take the right side of the circuit, we have R2, we have RL, and then we have V out, and we have V1 here that we just solved for above. So taking this voltage divider equation, we have V out is equal to RL over RL plus R2 times V out. I'm sorry, times V1. Okay? So let's go ahead and let's plug in what we've got for V1 up here into V1 down here. And so that'll give us RL over RL plus R2 times ZC over R1 plus ZC times VI. And we're in a good spot here. See, let's go ahead and divide by VI on both sides. And what do we have? We have VO over VI is equal to RL over RL plus R2 times ZC over R1 plus ZC. Okay, so what does this look like? This looks like what we defined as H of S before, as the transfer function. So we're in good shape here, but let's take it a step further. Remember we were talking about how ZC, the impedance of a capacitor, is actually 1 over SC, right? So let's clean this up just one step. So let's multiply the top and bottom of this fraction by ZC, 1 over ZC. And that will give us RL over RL plus R2 times 1 over R1 over 1 over the ZC plus 1. So you can see here, you know, this turns into 1, and then we got to distribute to ZC, which ends up being 1, and then R1, which ends up being R1 divided by ZC. Let me correct that here. This is just R1 over ZC. Right? Cool. Okay. So let's go ahead and now let's plug in 1 over SC into ZC. Okay? So that's going to give us RL over RL plus R2 times 1 over R1 over 1 over SC plus 1. Okay? And then this term here, we know that R1 is over 1. So we can go ahead and multiply by the reciprocal and get a proper fraction out of there. So by doing that, what we're going to end up with is, scroll down a bit, we're going to end up with H of S is equal to RL over RL plus R2 times R1 times C times S plus 1. Okay? So now let's go ahead and plug in. We have R1 is equal to 2K. R2 is equal to 1K. RL is equal to 1K. And C is equal to 500 nanofarads. Let's go ahead and plug in here. So this RL plus R2 is going to be 2K, right? And then this RL is 1K. So we have 1K over 2K. These will cancel, so we're ended up really with just 1/2 times 1 over R1 is 2K. And then C is 500 nano. Times S plus 1. Alright, so we have 2K, which is 2,000. This is coming from right here. 2,000 times 500 nanofarad is going to be 0.00000005. Okay, so let's go ahead and work that out. 2,000 times 0.6005 gives us 0.001. Alright, so this is going to be, this is equal to 1/2 1 over 0.001 S plus 1. Okay, just double check. Yep. Okay, moving on. This is almost a good answer. Some professors actually would take this answer, but we can let's take out a few terms and get it to where this this coefficient is gone. It's just a 1. So we have 1/2 1 over 0.001 then S plus, that's going to be what, 1,000. Okay, and then that's going to equal 1/2 1,000 over S plus 1,000. So combining 1,000 over 2 is going to give us 500 1 over S plus 1,000. Okay, so then that's it. I mean, that's a good answer right here. That's about as good as it gets. We can then the next part of the question was to get the type of filter, so low pass, high pass, or band pass. The way you do that is you're going to want to evaluate H of S at 0, and then
with its a limit approaching 0 and then its limit approaching infinity. So if we were to do that, if we were to say h of 0, where s equals 0, that's going to equal 500 times 1 over 0 plus 1000. So that gives us 1/2. And then for s equals infinity, or s is approaching infinity, we have h infinity is equal to 500 times 1 over infinity plus 1000. And we know when we have infinity in the denominator, that means it's uh, something really huge on the bottom, right? So this fraction actually becomes very, very small, so small that we can just call that 0. So this is actually going to be 0 as s approaches infinity. So let's just recap and remember what we said s was. We said s is equal to j omega, where omega is the frequency. So as s increases, that means omega is increasing, and as s decreases, that means omega, the frequency, is decreasing. So what it's saying here is that when you have a low frequency, down to DC, which is 0, we have this 1/2 gain. That's our transfer function gain. And then when we have very high frequencies, when s is approaching infinity, we have no gain, 0. So when something allows a signal through at low frequencies, that means we have a low pass filter. So we would have something that looks like this graph with h of s here and s, which is equal to j omega here. We would have this um, gain for everything below WC, or omega C, sorry about that. Omega C, which is the cutoff frequency. And the cutoff frequency of a filter is the point at which um, anything above or below the cutoff frequency, depending on what type of filter it is, it no longer is considered to be passing signal anymore. Or the signal has become so attenuated that the receiver of the signal is not going to be able to um, process it correctly, or it's going to, if it's a speaker, it's not going to play. You're just going to hear kind of noise or nothing. Um, yeah, probably nothing, because your signal is getting attenuated. So yeah, this is what we're looking at here. This is what the frequency plot would look like for this low pass filter, LPF. All right, everybody. Hope you enjoyed this video. Hope you learned something today. Um, as always, please like or subscribe and let us know down in the comments if you have any questions. Um, thank you. Have a great day.